Hello. So let's begin our lecture with energy diagrams. So in energy diagram, what we do, we take the total energy and the potential energy and plot both of them as a function of position. The whole idea of doing this is that certain key features of the motion of a one-dimensional system can be found using these energy diagrams. So what we will do, we'll begin by considering a very simple problem. We'll consider the harmonic oscillator. So our harmonic oscillator, we'll consider the one-dimensional harmonic oscillator. So the potential, which is a function of x, is given by half kx squared. So we'll start by sketching the energy diagram. So what we need is here is the horizontal axis, which is going to represent the position. So this is going to be the x. Then we have the vertical axis that's going to represent the energy. Then we will plot the potential function, and here the potential function is a parabola which is centered about the origin. So we have parabola centered about the origin. So this is half kx squared. Now we also have to understand the fact that the energy, the total energy of the system is conserved. The total energy, which is the sum of the kinetic energy and the potential energy. So this is fixed. So this is a constant value. So to represent E in this energy diagram, all we have to do is consider a fixed value of energy, and this is going to be a straight line which is parallel to the position axis or the x-axis in this case. So this is a energy. Now there's a certain region, and the motion of the particle of the object having this potential energy is going to be restricted within this particular region. So let's try to find out that region. So the point where the energy line intersects with the potential function, let's name it this point as x1 and this particular point as x2. Now this height is our total energy E, right? And the area under the curve from our knowledge of calculus, so this is going to be the function, the potential function v of x. So if we subtract the potential function from the energy, what we are left with? We have E minus V. That means we are left with the kinetic energy. So that means our kinetic energy will be within this particular region. So let me write down our kinetic energy T, which is equals to the total energy E minus the potential. So this is the region bounded by the energy line and the parabola. So this is going to be the region in which the motion of the particle is restricted. So this is a classic example of a bounded motion. Bounded in the sense that means at the center, when the position x is equals to 0, the particle is going to have a maximum kinetic energy, which is represented by this particular height. Now as it moves either towards the left or towards the right, then what happens is energy, the kinetic energy, is going to decrease, and then it's going to reach the point x1. The moment you reach either point x1 or x2, whichever be the case, its velocity goes to 0. That means it momentarily comes to rest when it reaches this particular point. These points are actually referred to as the turning points. So we have a turning point, one at x equals to x1 and another turning point at x equals to x2. So this is the point where the particle momentarily comes to rest, and then what happens, it changes its direction and again starts moving in the opposite direction. So this particular harmonic oscillator gives us a very good example of the bounded motion. Now this is our initial value of energy E. Let's call it E1. Now if we have a higher value of energy, so that means when the energy increases, so let's label it as E2, where E2 is greater than E1, then we can see that the distance between the two turning points are a little further apart as compared to the turning points in the case of E1. But whatever be the case, the particle is never going to be free. The motion of this particle is going to be bounded between those two turning points. And in another case, we can decrease the energy. Let's say we have an energy E3, and so suppose E3 is lesser than E1. And in that case, what happens? The amplitude of the motion is going to decrease, and if we further bring down the energy to the point where E is exactly equals to 0, then what we'll say, the particle now is going to be at rest at x equals to 0. So this is the case. Now, in our example of the harmonic oscillator, we have stated that the potential function is given by half kx squared. What that means, this potential function is directly proportional to the distance squared. So it increases indefinitely with distance. And this is also evident from our diagram. So as x increases, the potential value goes on increasing indefinitely. Now, what if the potential, instead of increasing, it decreases with distance? For that, we are going to consider a special type of potential that is due to the inverse square law force. Let's talk about that. Now here we have a potential V, which is expressed as a function of the radial distance r, which is given by k of r. So depending upon the value of k, the potential will tell us whether the central force is attractive in nature or negative in nature. So that means if k is positive, then we have a repulsive central force, because in that case the potential will be positive. And if we have k is less than 0, then then we have an attractive central force. Fine. Now let's try to draw the energy diagram of this particular potential function. So we have the y-axis, so this is going to be the energy axis. Then we have the horizontal position axis r. Now since this is 1 over r, so our graph will be something of this particular sort, which decays as r increases, and for values of r nearer to the origin is going to diverge. So this is the potential function v of r, which is dependent on 1 over r. Fine. Now we'll consider the value of energy. So let's say we have one particular value of energy, E. Now the energy is going to intercept these potential at a value, let's call it R minimum. We'll come to this in a moment. So this R minimum is referred to as the distance of closest approach. The total height, so this total height is the energy. Area below or area under the parabola will be representing the potential function. So that means if we subtract the potential from energy, so we'll be left with this particular region, and this gives us the kinetic energy, which is E minus V. Now we are considering a conserved system because this is the inverse square law force, so our system is conserved. So that means the energy is fixed. Now if the particle, let's say we have some particle that is being shot towards the force center, then what happens, as it moves towards the force center, it is going to lose some kinetic energy, which is evident from this particular diagram. So this is the initial kinetic energy, and as it moves closer to the force's center, its kinetic energy is decreasing. Now what happens, there will be a point which is the distance of closest approach, or R minimum, when the velocity is going to be momentarily 0, or it can say that the particle comes to at rest at this particular point. So this is the turning point, and when this particle reaches this turning point, then it's going to reverse its motion and then again move towards infinity. Now if we try to trace the trajectory of the system, then what we have here is, let's say this is our position R. So here we have R min, which is the distance of closest approach. So we have a particle which is coming towards the force's center, and at this point what happens, the velocity becomes momentarily 0, then it changes its direction and again moves back to infinity. So this is going to be the trajectory of the particle. The motion is unbounded here. The motion is going to be bounded when it's at the distance of closest approach, and then it's going to be unbounded for higher values of r. So in that case, we have a motion that is unbounded. However, for other values of potentials, and also depending upon the energy, we could have either a bounded motion or we could have an unbounded motion. To understand this particular fact, we were going to consider the energy diagram of a typical two-atom system. The y-axis is going to represent the energy, and we have the position represented by the x-axis. Now what we'll do, we'll consider a system that contains atoms, and if we have a very large separation between the atoms, then they are going to get attracted to each other very weakly with a force referred to as the van der Waals force. And this particular van der Waals force is so weak that it varies as 1 over r raised to the power of 7. Let's say the atoms are coming closer to each other. When they approach each other, then what happens? The electron cloud, and let's say they're more closer to each other, then what happens? The electron clouds are going to overlap, and this is going to produce some strong force, and the force could be either repulsive in nature or it could be attractive in nature, and it totally depends on the electron configuration of the atoms. Now supposing that the force is attractive in nature, so if our force is attractive in nature, then what happens? So we are reducing the distance between the atoms r. So that means we are going more closer towards the force's center. So what happened? If the force is attractive in nature, then the potential energy is going to decrease with decreasing r value. Now what happens? It goes, the potential energy decreases, but there will be a point. What happens that the atoms are so close to each other, then they are going to simply start repelling each other because of the presence of positively charged nuclear, and in that case the potential energy is then going to increase very rapidly. So there will be a very steep increase in the potential energy. So now what we'll do, we'll consider various values of energy. So here, let's say this is the value of energy E, which is greater than 0. So we will consider this horizontal axis, which also represents the position r. This represents the energy value of 0. Fine. Then we consider another value, energy E, which is lesser than 0. So we have 3 cases. Now for the first case, when E is greater than 0, what is happening? We will see a motion that is unbounded. That's because there will be a distance away from the force's center, which will be the, let's call it r1. So this is going to be the distance of closest approach. So you can say that for E greater than 0, this is an unbounded motion, and generally in such a case, the atoms are going very free to fly apart. So there is not too much of attraction happening. So that means the atoms are not binding to each other to form molecules. Here r1, which represents the distance of closest approach, its value does not change appreciably as our energy E is increased, which means that if we consider a much higher energy, let's say E prime, which is even higher than this particular value of E, then we can say there is not much change in the distance of closest approach, which tells us that the atoms behave much like hard spheres. So that means the distance of closest approach, this distance r1, it is not sensitive to the energy of collision. Now let's come to the other case when energy E is lesser than 0. Then in that case, so what we have here is 2 turning points. So in that case, the motion is going to be bounded for both large and small separation. So this is going to give us r mean, which will give us the distance of closest approach, and then we have r max, which is going to give us the distance of maximum approach, or the furthest distance from the force's center. So now that we have understood the energy diagrams for 3 systems, the harmonic oscillator, the central force system, and a 2-body diatomic atom, now we are well equipped to understand the effective potential for a central force motions. So in the previous lecture, we started out with an expression for the effective potential, which is a function of r, and that's given by the potential V of r, which is due to the central force, plus another factitious term, which is L squared over 2mr squared. So this factitious term is also referred to as the centrifugal potential, and that arises due to the centrifugal force. Now, what we will do, we'll try to draw the energy diagram. So on the vertical axis, we have the energy E, and we have the horizontal axis, which represents the position R. This is also going to represent the zero energy level, so we'll consider E to be 0 on this particular horizontal axis. Now, the effective potential is simply negative Q over R plus L squared over 2m R squared. So our fictitious potential, so this is dependent on 1 over R squared. That means it's going to fall faster compared to 1 over R. So that means if we try to plot the graph of L squared over 2m R squared, so it's going to be divergent near the origin or the force's center, and it's going to fall, and as R increases, the potential is going to drop down. And then coming to the potential due to the central force, now this has a 1 over R dependence, so it's going to fall, but it's going to fall slowly as compared to 1 over R squared. So it's also going to have a diverging value at near the origin, and it's going to sustain for a longer period of time compared to the L squared over 2m R squared term. The next task will be to combine the two terms, the central force potential as well as the centrifugal potential, in order to obtain a graph of the effective potential. Now, because the graph of L squared over 2m R squared is more dominant near the force's center, so when we try to plot the graph of the effective potential, so it is also going to diverge to a positive infinite value near the force's center, and then as R increases, it's going to go down and then slightly increase and go to 0. The next task will be to determine the orbit or the trajectory based on different values of energy. So let's consider the first energy, which is E1. Now remember that this particular system has an energy which is conserved, and because it is conserved, then it is going to be represented by a straight line which is parallel to the position axis. Now what happens next is a particle which is coming with an energy E1 towards the force's center is going to come as close as possible to this particular position. Let's call this R, this particular point. This will be actually on the position axis. This is going to be R1. Now it can never go, the particle can never go to a distance which is lesser than R1, because in that case what will happen, the potential energy, the V effective, that will become higher than the energy E1, and in that case when that happens, we can say that the kinetic energy is negative, and since that is not possible, so R1 is going to represent the distance of closest approach. So it is also going to be the turning point. So here the particle is going to come with a certain velocity, it will momentarily come to rest and then again change its direction and then go to infinity. So if we are to plot the trajectory of this particular particle, then it will look something like, so we have the position R, and let's suppose this is the force's center, and then we have the R1, which is the distance of closest approach. So the particle is going to come from infinity with some particular velocity, then is going to momentarily go to 0, and then it's going to change its direction and then again move back to infinity. Now the question that comes to mind is like, what will be the shape of this particular trajectory? For that, we are going to consider the expression of eccentricity. So we obtain the equation of eccentricity as the square root of 1 plus 2 times E L squared over mk squared. Right. Now in our case here, the value E, which is the energy E1, so that is a positive quantity. So here energy E1 is greater than 0. So this is greater than 0 means this entire term is going to be a positive quantity, which is again added to 1, and then we take a square root. So that means it gives us a value of epsilon which is always going to be greater than 1. And we know that when the eccentricity is greater than 1, then this trajectory is a hyperbolic in nature. So we have a hyperbolic orbit. So we have obtained a trajectory for the energy level E1. So this is a particle which is coming with a particular velocity. Then it reaches the distance of closest approach, which will be R1. And from there, it is going to change its direction and again move towards infinity in a hyperbolic orbit. While there is a lower limit to the distance r from the force's center, which is generally referred to as the distance of closest approach, up to which the particle can travel, there is no upper limit to the possible values of r. So that means the orbit is not bounded. So what we have here is the case of an unbounded motion. Now we come to the second set of energy when E is equals to 0. Now for the energy value E equals to 0, the trajectory of the particle is going to be quite similar, because we can see that the particle is going to come from infinity and then it's going to hit the centrifugal wall at, let's say, the position R2, and this R2 is going to be the distance of closest approach. And then from here, the velocity, which becomes momentarily 0 at this particular point, is then changes its direction, then again moves to infinity. The question is, what will be the trajectory of this particular motion look like? So we have epsilon given by, so when E is equals to 0, so epsilon will be equals to 1, and this is a parabolic path. So we can say, so we have R2, which is the distance of closest approach. This is the force center. So the particle is going to come towards R from infinity to R2 with a certain velocity. Then it's going to hit the centrifugal wall and then changes direction, then again move towards infinity. Now coming to the third case, what we'll do, we'll consider an energy. We'll call it energy E2. This will be the particular value of energy E2, and our E2 is less than 0, less than this particular E value. Now what is going to happen here? So here the particle is going to have a lower bound. So this is going to be R2. Now along R3, along with this lower bound value, it is also going to have a upper bound value, or the maximum value, which is going to occur at this particular point. So this is R4. So in that case, what we have is a bounded motion. So that means here we have two turning points. So one of the turning point is at R equals to R3, and the other turning point is at R4. The distance R3 and R4, also known as the apsidal distance. Now coming to the trajectory of this particular orbit. So here we have the energy value E2, which is less than 0, negative. So this value is going to be less than 1. So that means our epsilon value is going to be less than 1. And because eccentricity cannot be negative, so the lowest bound for eccentricity will be 0, such that our eccentricity value is lying between 0 and 1. And the only bound state which is possible in an inverse square force field with an eccentricity value of 0 and 1 is going to be an ellipse, or the particle is going to go in an elliptical path. So here we have an ellipse. So let's assume that the force center is at one of the foci. Then this particular length is going to be R3, and this particular length is going to be R4, where these are the turning points or the apsidal points. Finally, we consider another value of energy, which will be at the lowest point of this effective potential, and at that particular point the energy, which is E3, which is even lesser than E2 and negative as well, So in that case, the two turning points R3 and R4 are coinciding with each other. Since it's at the lower point, then we can say that the change in effective potential calculated with respect to change in R, where R is calculated at R0 and R0 is defined as the lowest point where the effective potential is going to be at its minimum. So this being the minimum value, so this is equals to 0. Now, if we differentiate this particular term with respect to R, since B is negative Q over R, so we have the dr of negative Q over R plus L squared over 2mr squared, and we equate them to 0, calculated at R equals to R0. After obtaining the derivative and solving this equation for R0, we obtain an expression R0 equals to L squared over m times K. Now, the angular momentum is a constant quantity, the mass is a constant, K is also a constant of proportionality. So here what we have found that the distance R0, which is constant, and whenever we have a constant distance, that means the eccentricity is exactly equals to 0, and this represents a circular orbit. So what we have done is, for different values of energy, we were able to calculate the eccentricity, and that helped us in finding out the nature of the orbit, like whether it is a hyperbolic orbit or a parabolic orbit or an elliptical or a circular orbit. So this is how we can use the concept of effective potential to determine the orbit of a path under the influence of a central force field. Thank you.